Hello everyone, my name is Metri Zughbi and I'm here to share with you the wonders of quantitative analysis of crack propagation in doped magnesium aluminate spinel. Yes, that is a mouthful, and yes, I had to practice it. First off, I'd like to thank my group consisting of Alexander Campos-Quiros, Dr. Animesh Kundu, and Dr. Masashi Watanabe, and the National Science Foundation, or more specifically, the Research Experience for Undergraduates Grant CMMI 2016279, because they're what made my research possible. Now back to the fun stuff. Magnesium aluminate spinel is a ceramic material that is as clear as a glass, but a lot lighter and a lot stronger. There's a lot of projected uses ranging from high performance and extreme condition windows due to its unique mechanical properties, and a variety of communication technologies due to its optical properties and transparency up to the mid-IR range. And I do say projected because currently Spinel is being manufactured using lithium fluoride as a sintering aid to help maintain density, which makes it transparent but causes it to become very weak due to grain boundary embrittlement. Our group is aiming to combat or overcome this embrittlement by using other dopant elements to strengthen those grain boundaries. Right now we are focusing on calcium and yttrium as dopants, which were chosen due to relatively low cost and their ionic sizes, which are larger than those of magnesium and aluminum ions in the spinel's crystal lattice. So, how do we do it? To start, we fabricate samples using high purity spinel powder with 500 parts per million of our desired dopant by sintering. Then samples go through an annealing phase, and after that perform hardness measurements to find certain mechanical properties. We use microhardness testing, which is done by using an instrument to drive a little squared diamond called a Victor's indenter into our polished samples. This creates that diamond shape you can see towards the left on the poster. This gives us an idea of how strong our fabricated samples are, and also, since ceramics undergo brittle fracture, cause 4 cracks to propagate from each tip of the diamond. Part of that crack is outlined by the little yellow box, and that's what I'm most interested in. As you can see in the bar graph on the left, results show that doped calcium brings no detrimental effects to mechanical properties of spinel samples, and although it isn't shown here, yttrium-doped samples share similar results. But after microhardness testing, we observed microstructures of the samples and applied grain orientation analysis, performed in a scanning electron microscope, or SEM. This allows us to analyze the submicroscopic grains of the spinel. Electron backscatter diffraction, or EBSD, is an SEM technique that allows us to view orientation distribution of grains as different colors, making it far easier to distinguish between the grains of the translucent or transparent samples. The EBSD images are taken and processed through Gatan digital micrograph software to determine how the crack propagates. So, in general, cracks will always want to take the path of least resistance, which we typically see by going either straight or trying to traverse between grains in the grain boundaries, since these boundaries are always weaker than the grain itself. The crack can either go through the grain, which is transgranular, or between the grains, which is intergranular. My primary job is to analyze the pattern that the cracks take as it travels throughout the sample. This is because if there's more transgranular fracture, which means there's, more through the grain boundaries are being strengthened by the dopants. This analysis is done by using the software to take horizontal slices through each of these pictures, and there are about 7 pictures per crack, and comparing the color of the grain on either side of the crack, which is that big black line going down the middle. And if the colors are the same, we say the crack is going through the grain. Now, this sounds great, but the process is only semi-automated due to limitations with the code and software. The code can't differentiate between colors, like seen on the picture on the right, so they have to be converted to a grayscale, which means complementary colors can show up as the same shade of gray. In addition, there are things like pores, which are these random black dots, and scratches that make more difficult for the code to get things correct, so there are copious amounts of spot checking that I have to do. But after all the pictures were analyzed, we compared the amount of transgranular cracking against the total crack length, and we normalize stuff to account for things like the scale of the image, the size of the grains, and, other fun stuff. This leaves us with a ratio of transgranular fracture for each dopant type, which is compared to pure spinel samples. As you can see with the line chart in the middle of the poster, even with 500 ppm of calcium, we see statistically significant differences among the propagation of each crack in the samples. And though not shown, changes were also observed in yttrium-doped samples. Lastly, to help ensure that the dopants were responsible for the change in crack propagation, X-ray dispersive spectroscopy, or EDS, was used in a scanning transmission microscope, or STEM, to determine that the element was found in much higher concentrations on the grain boundary rather than in the grain. Overall, grain boundary strength was preserved after doping calcium and yttrium in Spinel samples, and the presence of these dopants did contribute to a quantifiable difference in the amount of transgranular fracture and the crack propagation of magnesium aluminate Spinel samples. Thank you for the opportunity to present and share our findings with you all, and please let me know if you have any questions.